So just when you think the going gets good, I throw a curveball. Well, I don't. Organic chemistry does, not me. Don't blame me for any of this mess. Blame the textbook. They're the ones who tell me what to teach, and I just kind of go along with the flow. So, up until this point, we've talked about protonating the alcohol. We said that we're going to have to give this OH group a black eye and make it really ugly so that way carbon will boop, kick it to the curb. And we make room for another group to come on to its place. Now, here's the thing. This, of course, is not the only way that we can get rid of the OH group. You knew this was coming. I mean, you've been part of Chemistry 251. You saw all of the options that were out on the table for us to pick from, to make products from, and very many of them made very similar, if not the same, products. Well, here's no exception. We are working with an alcohol lecture. You know good and well it was just going to be more than one type of reaction. And if we look here on B and if we look on D, it's going to give us some insight. We have alternate ways to target the OH group right here and to get rid of that OH group. And we're going to have to talk about just a couple of different variants that we can choose from in order to eliminate that OH group and replace it with something else. So it's still a substitution reaction. It's going to go away, and it's going to get substituted with something else. So it's still a substitution reaction. Everything still goes according to plan, but we just have other options that we can, maybe from our Batman tool belt of organic reactions, choose from. Okay, so what are these, right? That's the thing. What are these two options? Okay, so the two that we're going to talk about, number one, is going to involve something called a phosphorus and I'm going to put halide here. So the trihalide is actually going to represent maybe tri means 3, so 3 bromines or 3 chlorines. Those are the typically ones that we see all the time. Those are the ones that we use all the time. So I know they say trihalide, but it's really a tribromide or a trichloride. It's one or the other. But we have to have phosphorus on this as well. So phosphorus is going to be the P. I hope you don't go PP in the middle of my video. If so, just push the pause. I'll wait for you, no matter how long that takes. All right, my second choice is not a phosphorus trihalide, but it's something called a thionyl chloride. Okay, so here is some language. Here is new definitions, new words that we can add to our vocabulary. Thio. Anytime we see the word thio in organic, that basically means sulfur. If I see a name that has thio in it somewhere, I'm going to probably automatically go to a place, and that place is a little old town called Sulfur. So thionyl chloride probably means sulfur, of course, with chloride, and this marriage takes place with the help of an oxygen, and we actually need 2 chlorines along for the ride. So SOCl2, that is going to be the thionyl chloride that we're going to be referring to. So phosphorus trihalides, PBr3s, PCl3s, or thionyl chlorides, which are SOCl2s. So the reason that we choose these, let's think about it for a minute, folks. We've talked about this point, getting rid of OH and replacing it with what? What have we replaced it with? If we were using HBr, if we were using HCl, the H would go on to the OH, bam, and give it a black eye, and then we would we would have bromine and chlorine left over. That is what goes on in the ugly water's position at this point. These are going to do the same thing. It's going to put on a bromine, or it's going to put on a chlorine, where that OH was going to be. Now, here's the thing. What's nice about these? What's nice? I'm going to put it in big, bold letters. There is no, I'm going to say it again, there's no rearrangement. You know, in those other example problems that we did with HBr and HCl, sometimes that OH group would leave in form of water, a carbocation would be left behind, the carbocation could shift, and if we're not careful and we don't catch it, well, that carbocation is going to shift on us and give us a product that we would not expect. And maybe we do not want it to do that. I mean, think about it. If you had a secondary, or let's just say secondary, because that's the one that's going to rearrange most, if you had a secondary alcohol, and that OH group left in form of an ugly water-leaving group, and a carbocation gets stayed behind, and that carbocation that stays behind will shift either left-handed or right-handed, well, okay, that's great and all. We can write that down on a sheet of paper. We can tell you what type of product that's going to be. But folks, listen, what if we don't want it to move? There's a possibility in that, right? In some of those earlier examples that we did, we were shifting carbocations and chlorines and bromines were going on in places that maybe we did not want it to go on. Here's your options. Here are two ways that you can have this reaction to go forward, and you are ensuring that rearrangement does not take place. So that's the good thing about these. Option 1 and Option 2, phosphorus trihalides and thionyl chlorides, do not allow rearrangement to take place. Bottom line. HBr and HCl do. If they're a secondary carbon, they're going to get a rearrangement if possible. So now you know why there's more to the story. Good thing about phosphorus trihalides and thionyl chlorides, again, it's a matter of what we want. Do we want to prevent that rearrangement? Do we not want it to move? And if so, this is the way we do it. Not with the addition of HBr, not with the addition of HCl. This ensures that wherever that OH group is going to be, that's where my halogen is going to end up. Something else to this, we need something here. We need to add something to these reactions. And what we're going to add is something called pyridine. All right, so here's the story with pyridine. It stinks. You talk about someone that's not had a bath in 2 to 3 weeks, all sweaty and grimy and filthy and disgusting. You know, it's kind of like Charlie Brown and Snoopy, right? There's that character on there that is always in a dust cloud because they stink. They're always dirty. Well, that's pyridine. Pyridine is always in a dust cloud. Wherever pyridine goes, you're going to know it because it's going to stink. Maybe so much that it's going to make you sick at your stomach. So that's the bad thing about these reactions. Can you imagine being in a closed-up laboratory, working with thionyl chloride or phosphorus trihalide, and they tell you, hey, go get the jar of pyridine. And then you go get the jar of pyridine and you take the lid off and woof! You're going to stink everybody out the room if you're not careful. So pyridine is going to be used, and it's going to be used as really a solvent. It really does not take part in the product formation. We don't see a pyridine product that gets formed. It's not really a catalyst, though, either, because a catalyst definition means it speeds it up. Well, pyridine doesn't speed the reaction up, so we can't call it a catalyst. Pyridine is going to be used as a solvent. This is a liquid that's going to be required for this reaction to take place. And the reason is because there's a chance that these reactions, whichever one I decide to use, could build up HBr or HCl. Folks, do you see a problem here? If I'm using these reactions with the sole intention to prevent rearrangement, and if these reactions are producing a product known as HBr or HCl, look at this. We've already talked about HBr and HCl. HBr and HCl could then come around and attack the organic that I am wanting to react with thionyl chloride or phosphorus trihalide. So we have to prevent the buildup of this. We cannot allow this to happen. If so, we're wasting our time. HBr and HCl is going to get generated in the reaction flask as this reaction goes forward, and then that HBr and HCl is going to turn around and do what it's always done that we've talked about up to this point. It's going to attack those alcohols. It's going to allow the rearrangement to take place, and then I'm just going to get a whole soup of nasty stuff that I don't want. So there has to be a way to prevent the increasing concentration of HBr and HCl, and we use pyridine in order for that to happen. Pyridine, because of that, you can regard this as a base, because this base will react with these acids and it will destroy it. Over time, it will completely destroy those, and that HBr and HCl is not going to be around. And that's a good thing, especially if we want to prevent rearrangement from taking place. All right, so what does the structure of pyridine look like? Well, this is going to be a ring structure, and this ring structure is going to be delocalized. There's going to be a double, single, double, single, double bond all the way around this ring. That is called a delocalized ring. Anytime that we had delocalization, one of the rules, double, single, double, cause you trouble. That's what we learned in Chemistry 251 with me. So double, single, double, cause you extra trouble. Well, not actually extra trouble. The molecules actually really enjoy it. They love it when delocalization's there, because delocalization will help stabilize the molecule. What this means is that if you have a delocalized network of double, single, double, these electrons can move around. It's kind of like having some kids, and you live in a safe neighborhood, and maybe mama or daddy wants some peace, and they open up the front door and they say, "Get out! Don't come back! Don't come back till 8 o'clock." Well, they turn their kids loose in the street and away they go, and they can feel good about it, and maybe they know it's a safe place. Other neighbors are watching out for them. It gets them out of the house. It gives them a little peace of mind. These molecules are the same way. Whenever they can turn their electrons loose and let them go run rampant through the molecule or the subdivision, these molecules really enjoy that. It gives them a little bit of sanity, a little bit of peace, maybe some downtime, pull up your feet, have a drink. That's what these molecules do with delocalization. But pyridine has one of these carbons switched to a nitrogen. This is the structure of pyridine. Now, that nitrogen has 3 bonds, 1, 2, 3, and we know from Chemistry 251 with formal charges that nitrogen really enjoys 3 bonds. And there they are. And that nitrogen will have 2 sets of electrons on it. How do I know that? Well, if you didn't learn that in Chem 251, or it's been a while, nitrogen has 5 valence electrons. From the periodic chart, that's the Roman numeral up at the top of the column. 5 valence. So this nitrogen has 1 bond, 2 bond, 3 bonds. There's minus 1, 2, 3. And then each dot represents another, 4, 5. So 5 minus 5 is a formal charge of a 0. That is why every time we see nitrogen, most of the time it's 3 bonds and a set of electrons. So this pyridine is thrown into the solution. And this HCl or HBr, it doesn't matter, they both happen the same way here, folks. These acids that get generated in the reaction are destroyed. And pyridine is the one that helps this out. How does it do it? All right, well, here's my nitrogen. Here's the HCl. HCl is a polar bond, just like before. We have a partial negative and a partial positive. Unequal electron distribution. That's what we have there. Well, this nitrogen has a free set of electrons. That's a negative area. That negative area would love to go to this hydrogen and say, "Psst, hey, come on over. I know you're not happy in that HCl bond. I know that chlorine's not giving you what you need. But hey, if you come over my way, then maybe we can form a relationship here and we can make things work out. You might be a much better, happier person because of it. Okay, well, that's great. And guess what hydrogen does? If you've had me for 251, okay. And hydrogen goes and does it. All right? It doesn't really think about these decisions beforehand, but that's exactly what it does. So in this mechanism, there's another step. This H and Cl, chlorine is a sucker. It wants those electrons. It's got some electronegativity to it. It's really close to fluorine on the table, isn't it? So that chlorine is going to suck everything that this hydrogen and chlorine share, and those electrons are going to go to chlorine. And chlorine goes, yay, I'm single and I'm free and I took your money and away I go. And chlorine might come back another day, but chlorine has what chlorine wants at this point. Well, what we have left over now is this pyridine ring, and there's the pyridine ring. It's still a double, single, double, single, double. There's still a nitrogen that's right here. We can't forget about that. But now there's a hydrogen on this system. Well, this formal charge now is a positive. Nitrogen bit off more than it could chew. Nitrogen realizes at this point, well, maybe I made a mistake. But you know what? I'm okay with this. Hydrogen's here. We'll make this work for now. Not a big problem. And we have chlorine that is now a full negative that has went off in solution. How do I know that this nitrogen is a positive? Well, nitrogen starts with 5 valence electrons, again, from the top of the column, Roman numeral 5. And this nitrogen has 1, 2, 3 from the bond. So 5 minus 3 is going to be a 2. And then it has one more from that hydrogen bond that wasn't there before. And this leaves us with a 1. So this is a positive 1 charge. This is what we call a formal charge calculation. This was something that was talked about in the very first chapter of the text that we use here at Cape Fear with our Chem 251 class. Okay, so this is how pyridine destroys the buildup of acids in our phosphorus trihalides and our thionyl chloride reactions. So, again, if you're an active listener, if you're an active thinker, this is going to be one of those questions that will pop up. Well, wait a minute. When we do these byproducts, this is a byproduct, and we've talked about the reactions of acids. Yes, yes, yes. Good for you. But now you know the answer to that before we even do one of our first examples. So let's turn to phosphorus tribromides, phosphorus trihalides, bromide or chloride. They all work the same way. It doesn't really matter. Let's do our first example with this. So CH3, CH2, and then an OH. We'll keep this alcohol very simple, a couple of carbons, and that's it. And we're going to react this sucker with a phosphorus trihalide. And I'm going to put the bromides on here. No apparent reason. Bromides are a little bit better than chlorides, but both of them work. PBr3, PCl3. They both behave the same way. All right, well, pretend for a minute that you're this phosphorus. And you're in a 3-way relationship. How are you going to keep up with it? I mean, you're going to get the names confused. You're going to get their birthdays confused. You're going to get the anniversaries confused. There's no way, unless you're a pro at this, that you're going to be keeping all of these relationships together. And in addition to that, all of those bromines, gimme, 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 gimme. It's that type of relationship, right? You've got a partner, and that partner really doesn't go out and do anything, and it just sucks your bank account dry. Who wants that? Phosphorus doesn't want it, but phosphorus is in a position right now that this bromine is going to be an electron sucker. This bromine, electron sucker. This bromine, electron sucker. And that spreads the phosphorus too thin. That's why this phosphorus is a partial positive charge. Out of the P's and the B's have a higher electronegativity from the periodic chart. That higher electronegativity makes them suck the electrons closer to their end, and this phosphorus now is very exposed. Boo-hoo, I don't have anything for myself. And that's a partial positive. So this oxygen is going to look at that phosphorus, and it's going to go, you know, if I could sweet talk that phosphorus, because it's kind of attractive, it's partial positive, I am attracted to it, it's got the right charge. If I could maybe attract myself to that phosphorus, and if I could sweet talk that phosphorus in getting rid of one of these bromines, then I could have another group that I could pull electrons from. That's all that oxygen wants. It's electron greedy, just like any other electronegative atom. Well, this is negative. We have an electron set, an electron set. This is a negative area of the molecule. That negative area is going to be attracted to that partial positive phosphorus. And that oxygen says, hey, come on over. And that phosphorus says, okay, just like hydrogen does. And in the middle of it, phosphorus realizes that it cannot take everything with it. So this phosphorus looks at this bromine and says, you've taken everything that I have, and you just need to go on away. Bing! Off it goes. All right, so we get some product formation that happens here. We're not yet done, but we're getting closer. We're looking at mechanism of the phosphorus trihalides. So we have the CH3, the CH2, and then the OH group. And this OH now has this phosphorus on it. And this phosphorus brought along for the ride two of the bromines that were there. Okay. Well, I'm going to switch these two groups around a little bit. I wrote it like this just so that you knew kind of what was going on. But I need to rewrite it just to make this mechanism step in the next part a little bit cleaner. All right, so I'm going to erase this hydrogen, and I'm going to erase this PBr2, and I'm just going to switch their places. Okay, PBr2. And a hydrogen that's here. So that hydrogen was the hydrogen that was part of this OH group from the very beginning. Okay? And as a byproduct, of course, we have this free bromine at this point. It's not a big deal. I don't really have to write this, but it's out there. It's swimming around. No one's forgot about it. But now we take a look at this oxygen-containing group. Because formal charge-wise, oxygen only wants two bonds with two sets of electrons. And now this oxygen realizes, whoops, I made a mistake. This mistake now has costed me an extra bond that I don't want. Well, here's the deal. Oxygen's getting ready to make a move. Oxygen's going to look at this and say, okay, I've got this carbon, and I've got this PBr2, and I have this hydrogen that's on here as well. If the oxygen decides to get rid of the hydrogen for some reason, then that hydrogen is going to pop off of the molecule, and that H and that Br is going to marry, and we get a product called hydrobromic acid, and that HBr is going to turn around and react with other alcohol groups from the very beginning up here at the very top. I do not want that to happen. So this is where the pyridine comes into play. I have this pyridine group, there we go, double, single, double, cause you trouble with the nitrogen that has the free pair. That is a base. That base is attracted to something acidic. This oxygen right now has too much, folks. Too much, too much. It's got to get rid of something. What does it decide to get rid of? Well, this base is going to come in, and it's going to go da-da-da-da-da-da-da-da-da-da. Ooh, a hydrogen here. I'm a base. I'm a proton acceptor. Hey, oxygen, do you want to get rid of your hydrogen? If so, I've got a good place for it, and it's my house. And that oxygen says, okay, here, take it. So that nitrogen grabs a hold of the hydrogen. The hydrogen gets ripped off, and the electrons between the O and the H have to go somewhere. So oxygen's electron greedy, and oxygen's the one that takes them. So this is the next step of that mechanism, and this is why that works. So pyridine rips the hydrogen from this, what was an alcohol group, and it leaves this ethyl group, CH3, CH2, with an OPBr2 in this step. All right, so what we have left over, we're still not yet done. We're still talking about mechanism here, right? CH3, CH2, and now an O with a PBr2 on it. Now, this OPBr2, we call this a bromophosphate group. A bromophosphate. And this bromophosphate group is so ugly. Oh gosh, it's so ugly. I mean, it's one of those things that you look at it and you just get nauseous. You get so sick at your stomach. I mean, you talk about the halogens being ugly. It's got nothing on that group. Now, remember, I said that we have this bromine that's out there, right? And that bromine is still here. So here's where a substitution comes into play. Because the carbon and this OPBr2 group, this particular bond right here, that carbon's going to look at that and go, oh my God. Oh, Jesus, I can't look at you. What have I done? Please, please just give me somebody that's not even halfway decent, a quarter decent. And that bromine is out there, and that bromine says, hey, I know I'm not the prettiest thing, but would you like to have a relationship with me? And that carbon says, absolutely. Absolutely. That OPBr2 is such a good leaving group, which means that it's so ugly, ugly, ugly that carbon doesn't want anything to do with it, with a 10-foot pole. So we have a substitution that happens yet again. It seems like that's what goes on with the alcohol groups, isn't it? So this carbon and this oxygen battle back and forth. Oxygen, electron sucker, electronegativity much higher than carbon, which means that this carbon is a partial positive and this oxygen is a partial negative. Well, that's good, because here we have this bromine that's negative. That's my nucleophile in this step. That negative piece is attracted to that carbon. That carbon says, okay, I'm cheating, but you know what? Even though you're ugly, I like you a whole lot better because you're prettier than this group. And it looks at carbon or oxygen and it says, you've wanted everything since the beginning. You're going to get everything. So take these electrons and shove them. Now go away and leave me alone. And that turns into a very good leaving group by definition. So here we have a substitution reaction that takes place. However, this step does not allow for carbocations. This step does not allow rearrangement to take place. Wherever this leaving group is going to be, that is where that halogen is going to attack. No rearrangement goes on, folks. Nothing. And this is how we get our alkyl halide, our CH3, CH2 with our Br. Now, I've just told you how this process works. Now, let's simplify it down a little bit. Okay? If I told you we're going to take CH3, CH2 with an OH group, and we are going to react this with PBr3 or PCl3. And on the arrow, you're going to see pyridine, because that is required for the solvent. I'm going to say what's formed. What type of product goes on? And you're going to look at this, and I know you're going to remember that mechanism. I know that you are. That mechanism's pretty important, right? No rearrangement, acidic hydrogens, pyridine's there to rip them off. The OPBr2 or OPCl2 bromophosphate group, chlorophosphate groups are very good leaving groups because they're so ugly. I know you're going to remember all of that, but we're going to distill that down. And what we're going to distill it into is this. If I give you, in this case, ethanol with the addition of phosphorus tribromide or phosphorus trichloride in the presence of pyridine, what kind of product gets formed? Well, I always start with my reagent. There we go. I'm going to look at this OH group. Pop! Bam! We give it a black eye, make it ugly, goes away, and in its place goes a bromine. Yeah, folks, it's that simple. If I added the PCl3 to it, guess what? It's the same thing. The PCl3 is the puncher that gives the OH, bam, a black eye. That leaves as not as a water molecule, really. We didn't really see that happen, did we? But it at least gives us a black eye. It makes it very ugly. And in its spot, we'll go with chlorine. And either one of those, guys, we've already talked about them. Bromine and chlorine are okay. It was much better than what was there before. But those are still ugly groups. Those are still good leaving groups. Carbon can kick those to the curb and not feel bad about it if something else pretty comes into the system. But this is another way that we can put bromine or chlorine onto an alcohol. Get rid of the alcohol group and put the halogen on instead. And then we can use these molecules and react them with something else in order to get what we really want. That's the kicker. All right, so there's the reaction of the phosphorus trihalides, either way, with bromine or chlorine. All right, so this is where we're going to stop this video. Now, in the next video, you know what's coming, because number 2 was a thionyl chloride. So we want to talk about the mechanism of the thionyl chloride as well. We want to talk about why it works, how it works, and then we'll kind of sum it up like we did right here with phosphorus trihalides. Just kind of give us an overall scheme of what goes on. The OH leaves, and a Br or a Cl goes into its place. No rearrangement happens. These are very easy products in order to determine and predict. All right, so in the next video, we'll talk about thionyl chloride. I'll be here when you're ready. Go take a break, crack those knuckles, get something to drink, get something to eat, use the bathroom. I'll be here no matter how long, again, it takes.